Okay, I think we can kick it off now. So welcome to the first in a series of three, this AI Virtual Tech Talks. This talk is about running accelerated ML applications on mobile and embedded devices using ARM-N. The talk's going to be given by James Conroy, and my name is Susan Engineer on the ARM-N team. My name is Jim Flynn. I'm the engineering manager on ARM-N. Have been for about the last year and a half or so.
Yep. So I'm James, and I'm going to be presenting the AI Virtual Tech Talks today. And as Jim said, it's all about running accelerated ML applications on mobile and embedded devices using ARM-N software stack. And as you said, I'm a software engineer working ARM-N. I've been here for about 2 years. And yeah, if we want to go to the next slide now and get it kicked off. There we go.
And that's what we look like. And yes, that is my passport photo.
I think that's my photo. I think it was from the second day. Mary, our office manager, took it.
When you were young and innocent.
Yeah, straight out of college.
Whereas I have been at this game for about 30 years. And before ARM, I was in a small company called Duolog in Galway that did design tools for electronic engineers that was purchased by ARM about 5 years ago. And that's how I came into the company.
Cool. So how are we doing on the participants there? Should we start her off, or are we waiting a little longer?
We've reached a nice round number, so, and we're about 5 minutes past the hour, so let's not keep people waiting. We'll kick off there.
Grand. So the AI Virtual Tech Talk series, this is just an outline of the upcoming schedule. The next one that's coming up September 20th is hosted by our partner Story AI, and how to reduce AI bias with synthetic data for edge applications. And then on the October 22nd, hosted by our own Navin Suda and Ling-Shuan Meng in San Jose at the office in ARM, they're going to present a talk on optimizing power and performance for machine learning at the edge, model deployment overview. So there are the two talks to keep an eye out for. You can use the link at the bottom of the screen here to sign up for them, and you'll be getting a link for those talks as well, like you have for this one as well. So the agenda for today, start off with asking the question, why ARM-N? Why you should use ARM-N for developing your neural network application. Then we'll give an overview of the ARM-N software stack. And then we'll give 3 ways you can use ARM-N. The first one being direct to ARM-N using the ARM-N interfaces. The second is using the parsers. So we have parsers that will parse the models that come from third-party neural network frameworks, such as TF Lite, ONNX, and PyTorch. And then the third main way of using ARM-N is through the Android NN HAL driver, which interfaces with the Android NN API. And we've got very extensive support in this area. We currently support Android Or that's just been released for both ARM-N, our ARM CPUs and GPUs. And then we'll go on to backends, and with a bit of focus on custom backends and dynamic backends. Then PiRMN, which is a Python interface and a way to how to use ARM-N through a Python API. And towards the end, then we'll just have a quick chat about the future development in the current release for the end of November, and how to get involved in the open source project, how you can contribute, how you can how the review the open source code review process works, how you can report issues, report bugs, and contribute by fixing any of those bugs or implementing new features in ARM-N. So why ARM-N? Why would anyone want to use ARM-N to develop their AI applications? So the first main one is that our parsers for open source frameworks such as TensorFlow Lite, ONNX, PyTorch, and Caffe, they enable rapid application development to the support of these frameworks. And we've got some very good coverage of the popular operators across all these different frameworks, and TensorFlow Lite we've got extensive support, and also through the Android API, we've got a very good support of the various operators, and we interface with that using our HAL driver to target ARM IP. And then for performance, which is what the main benefit that you get from ARM-N, and we'll illustrate that in the next slide. You can get some massive performance improvements through efficient targeting of ARM IP. This is using the optimized functions in the ARM compute library for ARM CPUs and GPUs, and also the Ethos-N driver stack, which is the supporting software around our recently released neural network processors. So the performance improvements in ARM IP is one of the main draws for using ARM-N. And this graph here, it illustrates the performance improvements across a range of different networks. We can see some of the popular image classification networks such as Inception v3, MobileNet, ResNet. One of the standout improvements you can see there on a big Cortex-A is 4.2 times on MobileNet v1. And this is all relative to 6 different industry software libraries. And at the bottom of that graph, then you can see the overall mean performance improvements across all the networks that we continually test. So you can see some very significant uplift in performance there. And this is an ongoing work that we're constantly trying to improve on. We're trying to constantly improve the performance uplift that we get across all our networks. And we're also working with our partners to improve ARM hardware performance on other software libraries. So now we've answered the question of why ARM-N, so we'll just go into an overview of what actually ARM-N is. So it's an ML inference API for Linux written in C++14, and it's an API to access many different neural network accelerated devices, such as ARM CPUs, GPUs, NPUs, and partner IP, which we're open to working with. And it's developed as open source, and external contributions are always welcome. At the end of this presentation, we'll talk about how anyone can contribute to our project. So on the diagram on the right, we can see ARM-N and the HAL driver, which is the main components of ARM-N highlighted in blue. And the HAL driver provides access to ARM-N for Android applications. And ARM-N then provides the backends for the lower level libraries and hardware drivers. So you can see in blue, we have the Neon backend, OpenCL backend, and that interacts with the ARM compute library, which has the optimized functions for executing ML workloads on Cortex-A CPUs and Mali GPUs. And we also have an NPU backend, which interacts with the NPU driver, and that's our pathway for accelerated ML workloads on our Ethos-N NPU processors. And as I mentioned, our Arm Cortex-A CPUs are accelerated for ARM v7 and v8 architectures, and our Mali GPUs are accelerated for Midgard and Bifrost architectures. So this slide is a more blown up example of the diagram is a more blown up example of the previous slide. We can see highlighted in blue is all the components represented by ARM-N, and the main parts that you can see there is the parsers, which interact with the third level libraries. Third-party libraries such as TF Lite, Android-N, Caffe, ONNX. And we also have the Android-N HAL driver, which interacts with Android-N. And down near the bottom of the screen, then we see the optimizer and the runtime. So these are the main parts of ARM-N. So like at a very high level, your application, you can either directly interact with ARM-N, directly use it. That's one of the flows that we'll talk about in a while. Or you can use one of the parsers to parse your model, which is generated from one of the open source libraries. Or you can use the HAL driver, but if your application is developed for Android devices. And once ARM-N has your model, it's been imported into ARM-N, then the Graph Builder API will start building up your network. A network is our way of describing a neural network graph. And this graph or network can be optimized. So based on your preferred backends, such as CPU, GPU, or NPU, it'll validate whether the various backends are supported on each of the different operators, and it'll create subgraphs which are separated by backend, and each of these subgraphs will be scheduled to run on any particular backend. So that's what the scheduler does in the optimizers. And finally, then the optimizer will do graph-specific optimizations, such as adding debug layers and target optimizations as well, which are optimizations that are done per backend. I'll just go on to the next slide now. So the use cases. The four main use cases: image classification. So these are the networks such as MobileNet or Inception, which will classify an image and with varying degrees of accuracy about what's actually contained in the image. Object recognition, which goes a bit further than image classification in that it actually identifies what's in the image, but also puts a bounding box around that image as well. So it tells you where it is, and it can recognize multiple different objects in a scene. And then another use case that some of you may not be as familiar with, which is super resolution. And this is illustrated on the diagram on the right, and it's typically used in TV, high resolution TV use cases where an image, maybe a 4K image or video, the video stream might be upscaled to 8K using an algorithm using a super resolution neural network. And then speech recognition. An example of this would be like word to letter. One of the networks that we support is identifying words in a speech, in a piece of speech that's like an MP3 file. So ARM-N at its heart is an open source project, and it's currently released under an MIT license. And we started ARM-N as a quarter release to ARM-N and the Android-N driver on GitHub. And we release since the late 2018, every February, May, August, and November each year. ARM Commute Library, which provides the hardware acceleration with optimized functions for machine learning workloads and ARM CPUs and many GPUs, releases at the same time to the Compute Library on GitHub also. And we moved to a continuously integrated development model for both ARM-N and ACL, And this means that when we were accepted into Lero as part of the official Artificial Intelligence Initiative, every commit to master is publicly available on the review on the mlplatform.org website. So it's a Gerrit review system. This means that us as ARM developers and anyone that wants to contribute to ARM, we all push our patches to the same area on ML platform. The code is reviewed in an open fashion, and once the code is reviewed, verified, it's merged into the master branch, and it's available for anyone to use instantly. And just a small note that we're planning to change our license from MIT to Apache 2 to provide clarity over patents to both contributors and users. So the release process, as I touched on in the previous slide, the master branch from review.mlplatform.org is automatically merged to GitHub. So all our reviews are done on ML platform, and when a patch is merged, that patch is merged the branch that's shown in GitHub. And releases are still made to GitHub every quarter as follows. The release candidate branch is created on ML platform. Release testing and qualification is done on ML platform until the candidate is certified. And once certification is complete, the release process is kicked off to generate documentation and release notes. And the final stage of release is to merge the release branch to GitHub and announce public availability. So now we'll talk about the three different ways, the three main ways that you can use ARM-NN. The first will be using ARM-NN interfaces directly. The second is through the ARM-NN Parsers, which give you access to the third-party open source frameworks such as TF Lite. And then we'll go through how to use the Android NN HAL driver to integrate with the Android NN API. So using ARM-NN interfaces directly, we start by describing the network and optimizing it. So using the iNetwork interface, construct the layers and the connections between them. And the diagram on the left describes that. So you first describe a new layer, add that layer to your network, connect that layer to the next layer in your network. And if you're not finished, you can describe your next layer and so on until you've built up a whole network. And once you're done, then you can call the network optimizer to allow ARM-NN to apply a known set of static optimizations to the network. And after that, then you can load the network and execute the inference by loading the network into the ARM-NN runtime. And then you can set your options, such as prefer backends. So if you have your preference for ARM CPUs, you could set that first. And if any, you could have a second preference, such as ARM GPUs. And then if there was any operator that wasn't supported on a CPU, it'll fall back to the GPU. And then you load the optimized network into the runtime, construct your input and output sensors, and then run the inference. So that's a way how to use ARM-NN directly using ARM-NN interfaces without the use of any third-party open source frameworks. So the second way that ARM-NN is typically used is through our parsers, and we have an example here of the TF Lite parser on how to load a test file, TF Lite file, which would be flat buffers, and how to create an iNetwork pointer network in ARM-NN using that TF Lite file. So you first create your TF Lite parser options, pass those options into the TF Lite parser pointer, and then using your parser, then create the network from the binary file that you supplied. And this network that we've created, the iNetwork pointer, this can now be optimized, and the inference is executed. Excuse me. And we deliver a test tool, execute network, to load and execute these models. And there's an example of how we can use execute network to run a TF-Lite binary file here. So you provide a model format, which in this case is TF-Lite binary, a model path, which is the path to your TF-Lite file, the input and output names of your tensors, the input tensor data, which in this case is a .snpy file, which is similar to a NumPy tensor or array. The only difference is that it's a 1D flattened array, and each value is separated by a space. And then the compute is given the preferred backends. So in this case, it's the Arm CPU accelerators. That's the first preferred backend. And the second is our CPU ref backend, which is a reference backend that we have. And then write outputs to file is where you output your output tensor. And then the third main way for integrating with PiRMN is through Android N API. And our HAL driver interfaces with this API. And in the middle of the screen, we have a command that will be run on an Android device. And this command is registering the driver with the 1.2 HAL driver with Android, using your CPU and GPU as your preferred backends. And once this is executed, any Android neural network API calls will be delegated to PiRMN. And if PiRMN doesn't support an operator that is in your network through the API, it'll fall back to the reference Android implementation of those operators. And if you wanted to do this through TF-Lite as well on Android, you'd create a TF-Lite interpreter and use NAPI flag on the interpreter to use the HAL driver. So backends, we're going to talk about the PiRMN backends and a little bit about custom backends and dynamic backends. So backend is an abstraction that maps the layers of a network graph to the hardware that is responsible for executing those layers. And each backend can support one or more layers from a graph. So if you have a network that isn't supported on a particular backend, that doesn't matter. If you have another backend that supports that particular operator, PiRMN will decide where to run each operator depending on which backend supports it. And you can create backend specific workloads for the layers of this port, and each layer will be executed using a workload, and the workload is used to enqueue a layer for computation. And PiRMN also allows statically linked and/or dynamically loaded backends. So custom backends. So the custom backends are backends that our partners can use to accelerate their own specific hardware. And PiRMN allows adding these custom backends to the pluggable backend mechanism. All backends must be uniquely identified by a backend ID, and this backend can have its own optimizations specific to the particular backend. And each backend needs its own memory management to optimize its memory usage, and the backend context notifies when a network is loaded or unloaded. Custom backends can also be loaded at runtime through the dynamic backend interface. And so more information about backends and custom backends and dynamic backends can be seen at the links below. So PiRMN is our Python interface that we recently released, and it's a way for Python developers to get familiar with PiRMN who may not be as familiar with C++. So it's a Python extension for the PiRMN SDK, and the interface is very similar to the PiRMN C++ API. It's built around the public headers of PiRMN, and all the operations are delegated to the PiRMN library. And it uses the Swig open source tool to generate the ARM Python shadow classes and C wrappers. And more information about PiRMN can be seen in GitHub at the link below as well. And the next slide, we also have 2 links about PiRMN, the README, and examples that you can try out yourself. So future development, we have a slide here about our end of November release, our 2011 release. So 2 main pieces of work that we're planning is usability and performance. And under usability, we're going to be releasing a Debian package verified for deployment on an Odroid N2 Plus board and Raspberry Pi 4, and also a TensorFlow Lite delegate. Excuse me. And a TensorFlow Lite delegate, which means that if you have a model, a TF Lite model, that the various backends in ARM may not support every operator, that this TensorFlow Lite delegate will allow us to delegate back to the Google supplied TensorFlow Lite reference implementations of those operators, which allow us to support a much wider range of networks than we currently do. And also we'll have an updated website and documentation with many more examples across a range of problem domains. And at the end of the presentation, there'll be an example of many tutorials that you can that'll help you get started with ARM. And performance. So under performance for this release, we have a fastpath option that we're going to be adding, which is winograd convolution optimizations. So this on ARM CPUs and GPUs, this will provide a performance improvement by optimizing the convolution filtering operator, and also the operator fusing and folding. We have various optimizations that are planned under this as well. So how to get involved in our open source project. So one way is to contribute code to ARM, and all code reviews are performed on the narrow ML platform Gerrit. So this is where ARM engineers and public contributors alike all contribute their code to, and all the code is reviewed in openly. And to create an account on ML platform, all you need is a GitHub account. So you use your GitHub account credentials to create your account on ML platform. So on your Linux machine, if you want to set up a Git repo with ARM, you'd git clone review.mlplatform.org ARM, cd into ARM, set up your username and your email. And setting up your name and email is important, because when you want to commit using sign-off, using git commit -s, Git will automatically sign off your commit using your name and your email address. And you can finally then push using git push origin head rest or master. And once you've done the git push, the patch will appear on ML platform Gerrit on that link there. And the contributor guide contains details of copyright notice and developer certificate of origin sign off. So even if you didn't want to contribute code to ARM, you could actually review code as well. And we're always open to people helping out with the code review process. Excuse me. So core contributors, such as ARM engineers, can give a +2 or -2 review and submit code. And all contributors can give a +1, 0, or -1 code review. So only core contributors can actually merge code to the master branch. And all patches require +1 verified from CI testing and verification. And it's all based on the Gerrit review system, which is open source. And the link there will show you plenty of information on how to use the Gerrit UI. And on the left here, we've just got an example of a GitHub issue that I was working on. And you can see in the Git commit title, I'm using GitHub hash 388. That's the format that's used to link with the GitHub issue number. And you can see on the left side the owner, which is myself, and the reviewers, the names of the reviewers. And you can see who reviewed the code and gave it a +2, that was Teresa, and the verify +1, which came from our internal CI system. And reporting issues then, so they're reported through GitHub. So if you found an issue with PiRMN, maybe if you were going through one of our tutorials and you found an issue, or if it was a specific issue related to a device maybe that we haven't tested before, you can report that issue in PiRMN first of all, and if you wanted to work on that issue, then you could work out a fix for it and then push it to ML platform. And here's a list of PiRMN tutorials then, under 3 different categories: configuring PiRMN for TF Lite and ONNX, then examples of various deployment techniques such as quantized TF Lite mobile v1 model, style transfer on Android, text-to-speech with Tesseract and PiRMN on Raspberry Pi, and accelerating ML inference on Raspberry Pi with a PiRMN. And then we've got also an example tutorial on building PiRMN custom backend plugins. So we've just got a little notice here about our DevSummit as well, Arm DevSummit, which is a 3-day virtual conference from October 3rd or October 6th to 8th. And there's a link there to register for the event. It's a 3-day conference, and we've got a rich agenda of 3 days of keynotes, 8 conference tracks, technical sessions, and community forum. So thank you very much for listening. We'll take questions now. Thanks very much. So, Jim, are we getting any questions in there yet?
So we have 1 or 2 have come in. One question is, does it work with Keras?
That's a good question, yeah. So Keras is an open source library that's used in the training of neural network models, and it can be used to produce TF Lite models. And so we support TF Lite models, which means that we can support Keras models if they're exported to TF Lite.
Next question is, which version of Raspberry Pi does it work on?
So we've tested PiRMN on all the Raspberry Pi versions up until Raspberry Pi 4, which is the latest version. But most of the performance improvements will be gained in Raspberry Pi 3 and especially Raspberry Pi 4, which have the ARM v8 architecture.
Another question here is, do you support TensorFlow, and if so, which versions?
Yeah, that's a good question, and I'll actually I'll go back to one of our slides to illustrate a point about that. So on this slide here, we can see at the very top we have TensorFlow, and so a TensorFlow model can be exported to TF Lite, and we support TF Lite models to our TF Lite parser. And we also have a TensorFlow parser that directly parses TensorFlow models, but this is soon to be deprecated. So the official way that we will support TensorFlow models in the future will be through the TF Lite parser by exporting your TensorFlow model to TF Lite. And the version of TensorFlow or TF Lite that we support is 1.15. And in a future release coming up soon, we will be also supporting TensorFlow 2.x.
So another one that's come in here is, what hardware is available that supports NPU acceleration?
That's a good question. So it's only about a year ago when ARM actually released the designs of our neural network processors. So there actually isn't any physical silicon yet, but we're working with our partners to actually get some real silicon for those devices, and that's all in the future, coming soon.
Another question here is, are there any publicly available ML out-of-the-box examples using PiRMN? Do we plan to release any publicly or to customers?
Yes, so in a previous slide there, the examples, I have, there's an accelerated ML inference in Raspberry Pi with PiRMN example there. And also, we've got examples of PiRMN on GitHub, on a GitHub repo as well.
Yeah, and I also know for a fact that the examples that are being produced for the website update for the 2011 release, every example that's going up there has a C++ version and a PiRMN version. So to show you how you can do it in either language.
Cool.
There's another one coming in. Do you support training?
We don't support training, no. So PiRMN is a neural network inference API for accelerated inference. So that's the execution of neural network models. So all the training is done, usually done with the open source third-party frameworks.
Do you support sub-byte data?
Sub-byte data. So is that it's quantized data? Is that the question? Maybe.
For instance, 1 to 7-bit.
So we support 8-bit, but we don't yet support 4-bit or, yeah. So I'm just looking at the questions coming in here. Yeah. So he said, yeah, we support 8-bit, which is the smallest quantization data type that we currently support, I think.
Yeah. Is there any profiling tool for ARM-N?
There is, Jim, you'd be an expert in that area. Do you want to chat with me about that yourself?
Yes. So ARM-N has recently added a profiling interface which integrates into what used to be DS5, the ARM Developer Studio. And currently you can get performance figures out, you can get counter values out, and performance layer performance figures. These for CPU, GPU, and a limited amount of data currently out of the NPU, and that the amount of data that's being produced there is going to increase over time as more profiling information is produced. So yeah, the preferred tool is DS5 to profile it. There is an internal JSON file dump you can also generate as well, which was the previous method of generating profiling information out of the library, and that's still in there. But the future is Developer Studio.
Yeah. And if there's any particular topics that any of you are interested, maybe for a future webinar, or any demos or tutorials that you'd like us to go through, please let us know through the Q&A also. Could be about profiling, or could be about PiRMN, or how to set up a custom backend. You can let us know in the Q&A also.
There'll also be one of our engineers presenting at the DevSummit. So if you want to go and ambush him, please do.
Go back to the DevSummit slide there. There's the link for devsummit.arm.com. As I said, it's a 3-day virtual conference. Loads of keynotes and technical sessions.
Yes, this presentation is being recorded, and the recording will be put up on the site.
Yeah, the website that this is released to is developer.arm.com, solutions, machine learning and ARM, AI virtual tech talks. So there you'll actually get a YouTube presentation link, which will be uploaded after this presentation, maybe in a day or two, and also the PDF to all the slides. Any more questions there? Feel free to pop them in.
How widespread is the use of ARM in industry?
Jim, do you want to give that one a go?
Ooh, I wish someone from marketing was here, but yeah. It's in use in a number of mobile platforms. So it's actively been used by some of the largest phone manufacturers as part of their framework, acceleration framework. I'm not sure how much I'm allowed to say. And it's, let me say, it's widely used and will be more widely used.
You can give the ballpark figure numbers, can be the kind of the sort of numbers that the number of devices that PiRMN is currently being used on, can we? It's in the region of millions anyway.
Yeah, it's widely deployed on a range of handsets from a range of the largest manufacturers, and that's just the mobile applications. It's also being used in a number of other custom kind of hardware applications as well.
Better use cases, yeah.
But I don't have percentage figures. Maybe we should try and see can we go get those kind of figures.
Yep.
From marketing. Any plans to support OR or M-class processors for edge inference? So the answer to this question is ARM-N is specifically targeted at A-class devices. If you're looking at OR or M-class devices, there's a separate library, CMSys, which is specifically targeted at those devices. And if you are interested in those devices, the previous series of tech talks, the previous 3 in the last quarter, we're concentrating on those platforms. So if you dig back into the website and look at the previous the previous talks, you'll get plenty of material on that.
Yeah, and one of those presentations, they also talk about our embedded NPU, which is used in conjunction with M-class processors, which is a very good talk.
So don't be shy. If you have any more questions, speak up there.
And also to mention, I don't know if you mentioned already, Jim, that one of our ARM-N engineers will be giving a talk at DevSummit also. So if they want any additional information about ARM-N or they have more questions, there'll be another opportunity to do that at DevSummit also.
Okay, it looks like we're we don't think there's any more questions coming in, and we're nearly at 5 to the hour, so we might call it at this point.
Grand, yeah. Well, thanks very much to everyone for logging into the call today. As I said, the ARM Dev Summit from October 6th to 8th is a 3-day virtual conference, which can be registered on the website there on the screen. Yeah, from myself and Jim, thanks very much for your time today.
And the recording of the presentation and the PDF of the slides will be up on the website shortly.
Yep.
So once again, thanks for attending.
Cheers.
And good luck.
Good luck.